enters the green region, and it's penalized when it enters the red region. So we're using sparse reward here. But the green region and the red region can be on either side. So, and the agent doesn't know that. And the only way for the agent to know the location of the green region is for the AND to enter the blue region. So this problem is challenging because we have to initialize the correct sequence of behaviors that leads to the green region just using the information in that blue region, and that's done through only sparse reward and the deep reinforcement learning algorithm. And in the end tag domain, we have, so sorry for audiences on that side, but we have an and an opponent that are initialized in the square region, and we make sure they're not too close together. And so the and is rewarded whenever it walks close enough to the opponent so that the opponent's inside the green sphere. But this task is also challenging because the opponent can move away from the AND robot, and the AND robot can only see the opponent when the opponent's within the blue region. So look at some learning curves here. So we have the 4 plots corresponding to the 4 domains described on the previous slide. On the x-axis, we have the number of time steps. So that's the number of interactions between the environment and the learning agent. On the y-axis, we have the success rate from 0 to 1. And the first thing we'll talk about is, so our method based on HAC, so-called HILMO, it performs on par or better than all other algorithms on the 4 domains. As we can see in the dark green curve, the green curves, and the other method, HILMO-O, which is very similar to our method, but it's based on a different base algorithm. It performs reasonably well on the door push and 2 boxes, as we can see in the yellow learning curves, but it doesn't learn very well in AND-TAG and heaven hell for reasons we briefly discussed in our paper. And for the flat and non-recurrent soft actor critic, it fails to solve all domains, so that's good to know. And finally, the hierarchical and non-recurrent hierarchical actor critic, which our algorithm is based off of, fails to solve 3 domains, but it learns a little bit, learns an okay policy on this one. So that shows that memory is actually critical for solving these problems. So 2 things to emphasize here. First is that the hierarchical algorithms take much less time to train, because when you're merging multiple lower level observations, your top level episodes are essentially shorter. And when you're feeding that into a recurrent neural network, that saves a lot of processing time. And another thing is that for our agent HILMO, as we can see on the left here, it achieves a much better state coverage after 500K steps. That indicates that, as we discussed in our paper, that it learns the lower level policy, a competent lower level policy much faster, which allows the top level policy to explore more effectively. And we want to show briefly the policies learned in the AND domains. So first we have the AND heaven hell. So the AND goes into the blue region following the pink square. So that's like the goal. And in AND-TAG, the AND sort of goes around trying to remember where it didn't see the opponent, and it sort of tracks down the opponent and try to tag it. And finally, for dirty laundry, the main one is that we need some form of domain knowledge to design the hierarchy. So like what part of the state should belong to the bottom level and top level, and how should we define the goal space for the bottom level. And we encourage ourselves and fellow researchers to think about like how to design a more general purpose hierarchical RL algorithm that we can just like throw at a generic problem to get better performance without much domain knowledge. Yeah, thank you.
right, wonderful. So now for our second talk, I believe we have Yazid Hassan, who's going to be presenting and getting set up. Sorry, remind me, I'll read out the title. It's the title of the paper is Flock Navigation by Coordinated Shepherds via Reinforcement Learning. Okay, so whenever you're ready, I think you should be able to use the mic, or you can take this one if you want.
All right, thank you. All right, so I'm here to talk to you guys about the work that we did where we used reinforcement learning to teach a group of agents to herd sheep. Now, reinforcement learning is a general algorithm, right? But we all know that in practice, it's hard to actually simply apply it to a problem. For example, if you're given a Markov decision process, you have your state action, your observations if it's partially observed, your reward structure, your transitions. Then with reinforcement learning, your agent can take actions, and through a feedback loop, you can estimate a policy or a solution. But in practice or in reality, it's not so straightforward. You have to do a lot of tuning. You have to figure out what your reward structure is going to be, what kind of observations are going to work out for you, what features are important. And if you're using a network to estimate, then you have to figure out that as well, your architecture, your algorithm, your input and output. And generally, whenever you get a new problem, you have to redo all this work. But if you have a problem that's similar to something that's already existing, then you can just reuse your formulation from that problem. The insight that we have is that you can map seemingly different problems to make them similar. So if we map one problem into the domain of another that is already solved and has a solution and a formulation, then you can use that formulation to produce a solution to the new problem. We showcase this by mapping problems that involve active and passive agents interacting, and we specifically look at the shepherding problem. Now, shepherding is a problem where your agents are guiding a group of herd agents, passive herd agents, towards a goal, inspired by real-life sheepdogs. It's a nice example of a complex problem because you have multiple active agents, so you have to consider their coordination, their cooperation, their communication, and there's also interactions between two different dynamics here. And it's a well-studied problem. A lot of solutions are existing where you have a driving point behind it, behind the flock, and you use heuristic or rule-based methods to guide your agents toward that point to push the flock. You also have solutions where you use quadratic programming to find solutions with guarantees. Reinforcement learning itself is also used often, but usually presented with some limitations like discretized environments or discrete actions, or even only dealing with 3 or 2 agents. But it usually gives some robustness to be able to handle, for example, obstacles. Other examples of active and passive agent problems involve oil spill problems, for example, where the passive agents are considered or dealt with as masses, or reach avoid problems where the active agents are supposed to hunt down the passive agents, or vice versa. And one particular problem we're going to be looking at that we're going to be using for the mapping is defender teams. In defender teams, you have a moving payload in an environment where you have a lot of obstacles that are moving around, and you have agents that are protecting you, or defensive agents. Now, this is a prior work of ours, and it has a solution and a formulation that produces robustness and scalability. So if we take a look at the two problems next to each other, how do we map from shepherding into the domain of defender teams? Well, we have our multi-agent partially observed Markov decision process at the bottom, and we can look at our state action pairs, and we can see that they're quite similar. They're both holonomic point masses, so they can move everywhere. And then if we look at our active agents in the shepherding problem is the shepherds, and we're mapping that to the defensive agents in the defender team. And we do the same with our passive herds to the passive pedestrians. And then the goal is going to be a special case of the payload that is not moving. Then our observations in the defender teams are 512 LiDAR rays, so they're range limited, and we have one channel for each entity type in the environment. So the point positions in the shepherding problem can be translated into LiDAR readings to be able to map into the domain. Now we're going to talk about a few things that are going to be different. The reward structure in the defender teams was meant to keep things out of the payload area. So in the shepherding problem, we're going to design a reward structure that motivates getting things into the goal. And this is the only bit of tuning that you actually need to do for this. And last but not least, the transition dynamics for the defender team problem is meant to simulate pedestrian movement, so it has social forces, whereas the shepherding problem has dynamics that simulate flock animals. So now that we have this mapping going on from between the shepherding and the defender teams, let's look at the formulation that it affords us. We're going to be using an actor-critic network. So it allows us to estimate actions and value, which is good because it's a continuous action and state space. So we kind of need that. And we're also going to be using frame stacking as input to the network. So the previous 3 observations are going to be concatenated and fed in. This allows us to infer velocity and acceleration. And lastly, we're going to be using sharing parameters between the shepherds. So each shepherd is going to have a copy of the network with the copy of the same parameters. During training, this allows for faster training because each of their individual experiences can be used to train the same network, which makes it faster. And during planning, this allows implicit communication between them. So just by seeing or observing each other's positions, they kind of have an idea of what each other is going to do. So they kind of cooperate that way. So we have that formulation and we apply it to here shown here 2 different flock models. On the left-hand side, we have a sheep flock model presented by Strombaum et al. And it represents, and you have each sheep trying to maintain distance to the center of mass. That's the behavior that's going on there. So it's a bit more tight. Where on the right-hand side, it's a Reynolds-Boyd's dynamic. So it's more mimicking birds. And the idea here is that it's maintaining the same heading as the as the rest of the flock. So if we take a look at what they're actually learning, here we have a mapped, the learned heat map value, or the heat map of the learned value. The blue areas representing higher or more preferred areas, and the red areas representing lower, less preferred areas. The big gray blob is the goal region, and the black dots are the active shepherds, and the white dots is the flock. And you can see here, it has a pretty, this is being trained, this is the one that's trained on the sheep agents. And you can see it has a pretty lean strategy. It wants to be behind the flock or next to its other sheep allies. But it generally wants to not be between the flock and the goal. But if we take a look at this map, we can see that when it's trained on the bird dynamics, it's a bit more stringent in strategy. Remember seeing that the flock was very hard to control. So it specifically wants to be very close to the flock and right behind it. And this both shows us that it can, this formulation produces a solution to different flock dynamics without even having to change the formulation or the reward or anything. Just through experience. So we conduct so now that we know that it produces a solution, we're going to see how good the solution is. We're going to conduct a few experiments and compare it to a few baseline methods. The baseline methods chosen here were ones that were applicable to the problem, so continuous state and action, and they drive the agents, the flock from a starting point to the goal and then keeping him there. On the left-hand side, we have a Strombaum-based method, which is representative of all the driving point-based methods. And then in the middle, we have a Pearson method, which is a formation-based one, and it's more concerned with a speed, so it tries to maintain the velocity of the flock. And then on the right-hand side is the DeepRL method. And just to point out, for all these experiments coming up, the DeepRL method was trained only once. So all the scalability and robustness is like evaluated without retraining. So the first thing we're going to evaluate we're going to look at the scalability of the method by evaluating the time it takes for the flock to get to the goal on the y-axis, and then on the x-axis we have an increasing flock size. And the line in the green is the DeepRL method, or the DeepRL shepherds. And you can see while it takes takes more than 25% more of the time, more time than the Pearson method to get the flock to the goal, it still takes about only 80% of the time it takes the Strombaum method. And if you take a look at this other plot, we're plotting the average path lengths of the shepherds. So if you're thinking about it's about efficiency. So if you're thinking about if you have